Please welcome our final guest speaker for this session, Mr. Riaan Carstens from Anglo American Platinum. We'll be discussing risk mitigation through effective monitoring. Riaan, if you can please come to the front.
Thank you very much and good morning to everyone. Thank you for the opportunity to present here today on your 15th birthday. And over the last, Jan, I think it's 4 or 5 years now, where I've been involved with Geotech in developing several of the underground systems that you're seeing, the SSP and the Compass that Paul just spoke about. And personally for me, it was really a rewarding experience having that opportunity to see how you take an idea from nothing, just an idea, and walking it through all the various processes until you get the fancy tool in the box. And what you don't see is sitting around a table here at Geotech with just wires everywhere to see how it works. Someone borrowing a broom handle from his wife's cupboard to put onto the SSP to go and test in a quarry up to the point where we got here. So Jan, personally from me, really rewarding experience, learned a lot of it, very enriching. So personally, thank you very much for the opportunity, having been part of the team and coming up with these solutions. And I think going forward, there's going to be a lot more opportunities to continue doing just that. So thank you very much from me personally. So the talk today is about risk mitigation through monitoring. And I'm going to talk more underground because I grew up in an underground mine, but you'll see that the concepts, the ideas that I'm going to talk about today will tie in nicely with what was presented previously, but it's equally applicable to open pits, massive mines, any mining environment that you go into. Okay, so let's start off with, so why do we mine? And what's the purpose of geotechnical engineering? So to put it simply, we create underground excavations to go and collect and mine valuable minerals. Paul spoke about it in his presentation about the minerals that we're mining and that we generate revenue from. So as geotechnical engineers, our impact is we want to take as most of that mineral that we can. So we want to maximize extraction, but we want to make it efficiently and as effectively as possible. And as geotechnical engineers, we play a huge part in any of those projects. So what do we do? So how do we achieve that? So first of all, we need to make sure that those excavations that we create on the surface or underground needs to remain stable so that we can get people and logistics into the mine. We can mine the ground and we need to get people and the valuable minerals out again. And through my presentation, I'm going to talk to you how we integrate monitoring in achieving this purpose. So general monitoring objectives. So why do we monitor? So firstly, it's to obtain data to inform our geotechnical models, and we use that as input into our designs. Once we start mining, it's to verify that the rock mass is behaving like we predicted, to monitor to confirm that, or if it's not, to optimize, change our input parameters and redesign. To verify that designs are effectively implemented, that's the dreaded compliance monitoring that a lot of geotechnical engineers have to work with on a daily basis, but it adds significant value. You've got to make sure you're going to have a great design, but we've got to make sure that that design is effectively implemented. Otherwise, the design won't work and you won't get the intended outcome. There's a lot of the monitoring on top. That is, the failure is going to happen. We want to warn people in the vicinity of the failure so that we can remove people and equipment to minimize the impact. Particularly true for open pit mining, where with the use of radars, where they've been very effective in withdrawing or getting people out of the way when the failure is imminent. Then in an underground context is to confirm support performances. The suppliers will tell you a support unit will do X. We need to monitor to confirm that it's actually doing that underground in terms of quality assurance. And then finally, if something goes wrong, to use that monitoring data to do a back analysis to understand what went wrong. And I suppose it links up to the second bullet point of verification of your input parameters. Now, if we look at risk assessment, it's constantly a balancing act between balancing risk on the one side and the reward on the other side. And this is something that I think geotechnical engineers deal with literally on a daily basis. And sometimes it's not easy decisions to make. There's sometimes a whole lot of pressure to go and mine extra to get value in the short term. And geotechnical engineers generally are put under a lot of pressure to make those kind of decisions. So on the one hand, you don't want to be too aggressive, because if you do that, there's consequences in terms of injury to people, fatalities, loss of equipment, impact on production. But on the other side, if you are too conservative, you destroy value. And there's lots of examples also in the industry where we have destroyed significant value. If you think something like the Hedley and Grant pillar formula, if you're too conservative, you destroy revenue and value. So you've got to get to that balancing point where it's not too conservative and not too aggressive. And monitoring and continuous monitoring plays a critical part in achieving this outcome. Now, the way that we manage risk in Anglo-American, well, all of the Anglo-American mines, is we start off generally with a baseline risk assessment where you identify your major risk. We call it priority unwanted events. One of those would be fall of ground, but it will include things like explosions, gassing, falling from heights, etc. Then we take that, and in our case, priority unwanted event, and we use a method called a BowTie risk assessment. It's a BowTie because it looks like an old-fashioned bow tie. Now, in the center of the bow tie is your top event. This is the thing that you want to prevent. And in our case, we want to prevent unplanned and uncontrolled falls of ground. Now, on the left-hand side of the bow tie, these are all your threats. These are the things that if that goes wrong, it will lead to the event, to your unplanned and uncontrolled fall of ground. And these things include, and in our case, it's things like inadequate mine design, inadequate support design, exposure into unsupported ground, inadequate support execution, and not mining according to plan. Now, for each one of these threats, you then develop what we call a series of controls. So let's say, for example, inadequate support execution means support are not installed as it's supposed to be. So the first thing is, your first control is support's installed. It's things like fit for purpose equipment. It's training of people. It's making sure the logistics, the stuff that they need is there on time. They've got sufficient time to do it. So there's a list of controls that are then defined for each one of these threats to prevent it. And if you comply with all of that, it should prevent that from happening. And some of these are then defined as critical controls. So critical control is that last thing. If that is in place, the fall of ground won't happen. So a simple example again is if I've got a wedge sitting in the hanging wall or the side wall of an excavation and there's sufficient bolts going through it, it should not come out. So the support that's installed in our case is our critical control, and we've got several of them. On the other side of the equation of the bow tie, is when things go wrong. So the event is going to happen. You can't stop it anymore. And it can lead to injuries, fatals, damage to equipment, loss of production. And this is now about trying to mitigate the consequences. Things like in open pits, like that I said earlier, is your radar system. So you can't stop it anymore. The wall is coming, but at least you've got early warning that the failure is going to happen. So you've got time to withdraw people from the area so you minimize the impact of the failure. Similar systems in place underground, either in terms of warning devices, but not as effective because fall of ground has got very different dynamics compared to an open pit that generally gives you time to get out. Now, if we look at our critical controls that we came up with in Anglo-American, and this is now critical controls across the whole of Anglo American. So this is not just Anglo Platinum or De Beers or Chile. This has now been standardized across the whole of Anglo American. These 5 for underground, these 5 critical controls. Interesting story, when we did this the first time, we came up with 29 critical controls. Then afterwards, fortunately, sanity prevailed and we sorted out how this thing works. So can you imagine trying to manage 29 critical controls because everybody thinks everything is important? We whittled it down to these 5. 2 talks to design, those 2, your mine design and your support design, which sits fairly and squarely within the geotech space. There's 2 about implementation, mine to design, support to design, and then 1 is about barricades and exclusion zones. So if you get to the point where you can't handle it anymore, you put up an effective barricade and nobody goes beyond it, nobody gets exposed to that. And what's important is that you need to continuously monitor the effectiveness of each one of these controls. From the start, if you look at the design, from the point where you start designing, monitoring starts. And I'll explain it a bit more in the next slide. So if we look at a very generalized design process flow, so we start off with, Paul mentioned it, we collect a whole lot of data, call it data collection, and that's the stuff that we put into our models, input parameters into the fancy numerical models that we run to show the nice colors and contours of how the rock mass will behave. Then we design, we implement, we make the holes in the ground, then we start monitoring to see how it's responding. Based on that, we optimize. Now, generally, and maybe it's my personal opinion, when we think about monitoring, this is where we're at. We think monitoring sits there. We've got to make the hole in the ground first. So once we've made the hole in the ground, monitoring starts. I've got a different opinion. I think monitoring starts right at the start. We call it data collection, but in essence, it's nothing else than monitoring. So when you start with a project and you fly an aeroplane over it to do the aeromags or the seismic surveys, or we drill holes in the ground, we put instruments in it to measure all sorts of things, it's nothing else than monitoring. We just call it data collection. But that to me is where we need to start with the process. And then we never stop. Monitoring starts when we begin the project and it continues past the point where we close the mine. I've worked on several projects now. I was fortunate to work on several big projects for Anglo over the last 3 years. And what you find is when you go back, people collect data for the first part of the project, and then they stop. They start mining, and then there's bits and pieces of monitoring that happens to verify things. Some companies are better than others, some mines are better than others. But generally, the process is a bit disjointed. You find the data all over the place. There's no single database that you can go back to go and collect the data. It is spreadsheets on computers everywhere, and to find it is difficult. And I think it ties into what Paul said earlier. All of a sudden, we're getting data and we're getting lots of it. And it's going to be critical going forward about how we store and manage that data. And this brings me to my next slide, which is probably the crux of the design. Now, the open pit guys will be more familiar with this. I borrowed this from the LOAP work. But it talks about that geotechnical model that you set up when you start the mine. Now, it consists of 4 parts. Top left, you've got your rock mass model. You need to understand everything about the rock. That's our steel and concrete that we design in. We need to understand the strength of that material that we're going to mine in. You need to understand the geology, your lithological model. What is where in the sequence of where you're going to create the open pit or the underground excavation. And then the next one is your structural model. Really understanding major structure and your minor structure that makes up this rock mass. And I think the open pit guys are probably better. A lot of effort that still needs to come in the underground space in understanding our structural models and the basics of structural geology. And then obviously hydrogeological models. I mean, it was shown earlier today. If you get the water wrong, you don't understand the water specifically open, but significant consequences. From an underground perspective, I suppose understanding your hydrogeological model, more about mine flooding. You don't want to mine into a body of water and flood the mine, understanding where your water is going to come from, but also here understanding the makeup of your water, specifically how corrosive is your water. And I'm not going to try and guess how many mines actually knows where the water is coming from underground and how corrosive that water is, because we start these mines and they last for 50 years. And you've got to take into account if that water is corrosive, when you do your design up front, you've got to understand you've got to design for 50 years here, or you've got to build in some rehabilitation along the way. So for me, this is the crux of the geotech design, and monitoring permeates through all of this from the start of the project. And once you implement, you've got to continue monitoring each one of these aspects to make sure that what you had in the beginning of the design is still relevant. Or when things change, you need to pick it up quickly so that you can adapt your design. That is where the most effort needs to go into in ensuring that we've got stable mines that we can mine. Obviously, with this gives you now an understanding of your failure mechanism. You add your loading conditions and off you go and you can do your design. Now, if we think of some of the systems that we've got currently at operations and in the industry, I would say this is probably the benchmark, Seismic Systems in South Africa. If I have an event at our operation at Amandelbult, literally within minutes, we know the magnitude and we know where it is. And that information goes from Thabazimbi underground all the way up the infrastructure. It reports here to Stellenbosch, to IMS, where they do the final processing, back to the control room at the mine in 5 to 10 minutes. So for me, this is, in terms of underground gold mining, this is the gold standard. Geophones pick up big particle velocity. It's copper wires. We fancy now some modems and some onto fiber backbones. But still, just think of it. An event happened at Thabazimbi. 5 minutes later, we know the magnitude and we know the location, so that we can, if we need to, initiate emergency rescue operations if it should require. And then obviously the data is afterwards used for back analysis. I think Paul has covered some of this, but what we're currently using, starting from the left, is downhole geophysical tools. Again, privileged to have worked with on a lot of projects the last couple of years, and this is an area where there's this wealth of data and information that we can use for our designs, but are not currently utilized fully in the industry. You get information of rock mass strengths. You can get information on magnitude and orientation of stresses. There's a lot of knowledge and skills outside of South Africa in the oil and gas industry that uses these techniques regularly, and for some reason we've never used it in South Africa. In Anglo, we've started to use it now, and there's significant amount of value in it. You can pick up all your structures. You can pick up orientation of those structures. So this is an area where we're putting a lot of focus going forward into making sure we get all the data that we can, which I said subset of monitoring that goes into our designs. The next one is a product from Groundwork. It's a continuous closure station. We use that to understand how the rock mass is behaving for two things. One, calibration of numerical models, but a lot of it goes into support design. So I want to know what's the closure, what's the rate of closure, so that I can put the right type of support in to cater for the rock mass response. The borehole camera, Paul covered it, to typically look into your hanging wall to see where there are specific markers that is of interest, or whether any deformation or opening up has happened on any one of those discontinuities. The one here at the bottom does similar thing. It's a multi-point borehole extensometer. Also, you know the boundary of the excavation is moving, but this gives you an idea of what is moving and where it is moving. So you can target specific failure planes within the boundaries of your excavation. And these two you're familiar with, the SSP, and from that developed. When we were trying to solve that positioning underground, and they told me about the accelerometers and that there's something else in this thing. I can't remember his name now. I thought, but someone told me that's the exact same things that's in a cell phone. So that's where the idea was born. Let's try and develop something that's purpose for underground, fit for purpose for underground, because on a lot of mines, there's issues with taking cell phones underground. The next set of monitoring equipment is more related to the TARP type. Now, this is where things are going to go wrong. You want to warn people in the immediate vicinity to get out. From the left-hand side, that's a product from New Concept Mining, the Fox stick. It's got those LED lights on it, so you set it. If it exceeds a certain threshold, it will turn from green to orange to red to tell you that you've now exceeded a certain deformation. There's another company that produces a mechanical unit as well as also an electronic unit. The mechanical unit is it anchors at the back. If there's deformation, it will trigger and a luminescent stick will pop out at the bottom. Where this one, there's lights there that also change color. And then there's one that most of you are familiar with. It's called the fog light, also installed in the hanging wall or the sidewall. It's got a cam at the back, some electronics in front, and this flashes green and goes orange and red based on your top triggers. Okay, some school fees. So I personally paid some very expensive school fees in trying to set up some of these monitoring systems underground. And here's some learnings. These are for free. Stakeholder involvement. Make sure that everybody in that working place knows what you're doing, what's the purpose of the monitoring. It does not prevent tampering or destruction of your unit, but it limits the likelihood. Okay, so if people understand and the purpose and why you're doing and what's the benefit to them, it at least reduces some of the risk that someone comes and takes the thing out, go down next week after all that effort and the thing lies in the gully or lies on the footwall. You really need to think about the integration of your mining method. Where will what move? Because Murphy has it, you put your thing in and here comes the machine and that's where it wants to put its stinger and it destroys your cabling and everything down, you have to go back and fix it. So you've got to really do a risk assessment and think through that process. Where does what move? And if you need to run cables, where will those cables run to make sure that it doesn't get into the way of scrapers and people and machines? Power. So you need to think, how long does this need to last? If it's got to last several years, batteries is not a good idea. So coal mine, that shall not be named, started putting these things in, and in a coal mine, they move at such a speed, every intersection, and 1 year down the line, the battery starts dying. Now, the system and the management to try and go and replace batteries at that magnitude becomes impossible. So think about how long does this thing have to last? If it has got to last very long and you can't manage batteries, go mechanical. If it needs power, then you've got to give it a power source. Batteries for long term, maybe not such a good idea, at least not with the battery technology that we've got now. So remember that. Access to your service or to the cloud. Now, every supplier that will come to you will show you the fancy graphs to say from underground into the cloud, and you can monitor as it moves. You put it in underground, start monitoring, and you say, I want to get it into the cloud, and then you run into your IT department. And he says, no ways. This is not going through my firewalls. And then it becomes literally, I see people laughing in the audience, it takes you months. I thought it should be easy. The IT just says, yep, it can go through here, in here, into the cloud. It's not so simple. So important, stakeholder involvement. Don't forget your IT guy. He's quite important in this process. He needs to be there right up front so that he can see how do we get these things through all the servers and the firewalls, because let's face it, cybersecurity is a major issue and they are I would say, paranoid about people getting into you and getting access to your data. So you can understand it, just make sure right up front that you get them in. And then I think Michael will talk to this probably as well, mechanical verification. So with all this electronics, very fancy, very convenient, brings a lot of functionality. However, you still need to do some form of mechanical verification to say that this electronic device is 2 millimeters. It's not 5 millimeters. So make sure that you bring in mechanical verification when you do monitoring as well. Okay. So the next half of my presentation, I'm going to take you through some of the, what I think it's very exciting projects within Anglo American, and how we're trying to, how it impacts on monitoring, the way that we're going to do monitoring going forward, and how we want to integrate some of these monitoring tools in the way that we're going to mine. So the first one is underground scanning. Technology has advanced significantly. If you look at the photographs, that photo, that's the scan. It's almost, it's identical. The amount of detail that you get out of the scanning technology is amazing. And our vision is that going forward, that every single working place on a daily basis will get some form of a scan. Currently it's laser scanning, but I mean, there's lots of technology, photographs, video, acoustics, infrared, but for now, our focus is on 3D laser scanning. And what we want to do with that is, first of all, collect rock mass data. So the software already exists that I can take the scan and I can do mapping from it. So I can get different direction of structures. I can see where my wedges are, input into my designs. I can do rock mass ratings from this. I can do support compliance checks. It picks up the support. I can measure it against a standard and it'll tell me automatically, yes, we're complying, yes or no. Quicker turnaround on TARP triggers. One of the big things about underground is accessibility. So someone will trigger a TARP. It means they have to stop for their day. Geotech will go underground the next day and then need to give advice. Obviously, if production pressure gets ramped up, the likelihood of triggering a TARP comes down because inevitably you lose a blast. And from a business perspective, not just from a safety perspective, significant loss of revenue because you've got to stop and only the next day can you get people there. And then the last one is design reconciliation, is to check that we're mining where we're supposed to, in space. Also sizes of excavations, it's not too big or too small, that, especially when it comes to pillars, etc., that we can do that reconciliation much faster and much quicker. Generally now you've got to wait until the end of the month, till the surveyor gets there, then he tells you, then they mine 40 meters, now you've got to fix it. The idea is to start getting this data quicker so that we can respond quicker. Pick it up early and fix it before it becomes a major problem. Okay, this is just a simplified sketch illustrating the concept. So on the left-hand side, I mean, we're looking at various technologies now to capture the data. From robots to drones, all the type of scanners. We've got a dedicated site now at one of our mines where we've put in all the fiber backbones now. We've identified a specific area where we've now put all the current scanning technologies out there. We've put them through that. We've taken the scans of the areas, and we're now at the point where we're trying to see, so how do we take these different parts now and put it into the system? Because the idea is we'll scan underground. It will be communicated by some means to surface, where you will have a geotechnical specialist looking at the data, either on a computer screen, or this is where I think we're going, augmented reality. And to be able to, that same day or within an hour, give feedback back to the person underground to say, this is what you need to do. Now, the other day I was exposed to this technology and it's mind-blowing. So my picture that I've got in my mind of how it's going to work in future is the miner will pick up something underground. You'll have some scanning technology which you will scan that area. I will stand on surface with this pair of glasses and I'll be able to walk into this design. It's possible, it's already there. Where I'll be able to walk into that tunnel, look up at what he's seeing, walk out of the tunnel, look into the hanging wall, into the side walls, and give him a recommendation of what he should be doing. in real time. I think with the connectivity that's coming in our underground mines, this is the future. Either some form of augmented reality or some form of virtual reality, but I think that's the dream. I mean, I was having a discussion with Heinrich the other day where he said the drill operator in Canada, sitting in Canada underground, phones him in South Africa in the morning, takes out his cell phone and shows him, I've got a problem here, and Heinrich can respond on his cell phone, sitting in South Africa, I think you need to do this, this, and this. All the, let's call it all the Lego parts, in my opinion, is there now. We've got the scanning technology, and that will improve. We're starting to get the backbones. We've got all the software and the technology on surface to analyze and give recommendations. The key thing now is going to be putting this together, and that's the next step of our trial that we're looking at now. We've got the scans now, so now we're going to see how can we actually put this together in a system that it's sustainable and that it works, because the data, unfortunately, big data sets, and we now need to see, probably start off by every week and then starting to get to the dream of getting a scan on a daily basis. The next set of technology, ironically, that we're looking at, yesterday I think you saw it under the stairs, is to look at the device, some sort of device, that we can give the driller on the face or where people are working. I want that device, I want to put it down next to him. It starts scanning, create the baseline of what's happening around it, and then continue scanning. And if something moves, it needs to warn the driller. Because let's face it, we're not fully mechanized yet. There's a lot of narrow reef, conventional mining still taking place where someone sits on the face with a machine and drills into that face. We're going to modernize it, yes, as Paul said, but still you've got someone sitting there drilling into that face. And our idea is we need to get something that we can put next to him. If it triggers, either linked to its cap lamp start flashing or to in-stope lighting to say, get out of the way, something's moving, you need to move out. Might not stop the fall of ground, but we want to get the people out if that is imminent. The last project is, over the last, I think, 3 to 4 years, there's been a lot of research in Anglo about cutting technology, hard rock cutting technology. We've collaborated with Sandvik, a company called Sandvik. This machine is called the MN330. It cuts this version. The first one was a smaller unit. We just made sure, can we cut UG2 specifically, 80 to 100 MPa. And this is the new one that they're currently busy. We're starting mining probably next year, February, at one of our mines. Cuts a 1.5 meter slot, 6 meters wide. Then it comes back and it cuts another slot. Up. So you create a top axis, bottom axis, and it will cut from bottom to top. It's got a big vacuum system behind it that takes all the chippings out back to surface. So what we want to do here is, I'll explain this in a bit more. This is the machine. Let me just go through it. So in front here, you've got the cutting mechanisms. There's the cutter. It swivels left to right. It takes about 0.8 meter cut incrementally before it moves again. And at the back of the unit, you've got a bolting unit, canopy where the person sits that will do the bolting. And what we want to try and do is integrate the subsurface profiler into this bolting unit. So this is concept still. The idea is that these SSPs will be fitted next to these bolting units. This whole mechanism, this canopy, moves left and right. So in the off position, the SSP will be down. When they stop again to start cutting, it will go up and you will scan left and right. There will be a tablet available for the person sitting in this canopy. But at the same time, we want to take that data, put it onto the fiber backbone, because this thing is remote controlled almost, to get that information back to a control room on surface so that we consistently see. And in this case, we want to see where the triplets are sitting. Triplets is a chrome stringer in the immediate roof, and we want to know, because if it goes too far or too close, we need to change our support system. And we also want to pick up to see whether we can pick up jointing. Now, cutting is fantastic. It's God-gifted geotechs, because nothing falls out. But because nothing falls out, you can't map anything. you only see a line on that hanging wall. That's all you see. You see one line, and if you don't see it in the sidewalls, you've got no idea where that thing is dipping. You only literally see that joint line on the surface. And we want to use the SSP for that also to give us an indication, the angles and where this thing is dipping into the roof of that excavation. This is just a close-up view. That's in the yellow will be in the down position. Once it's stopped, flipped up, and then it will scan left and right. There's some writing there on the left, but I discussed that already. So as I said, just another indication of the scanning. And here's a photograph in the factory currently where the machine is in its final preparation. There will be a tablet with a guy sitting in the bolting unit that will be able to see what comes from the scans as well as it going to surface. Okay, second last slide. So I think Paul mentioned it. So how are we going to manage all this data? Because it's not going to become less, it's just going to be more and more data. With us being connected and everything, if we can achieve everything that we want to do, we're going to sit with a lot of data that we have to manage. This project, we call it our Digital Ground Control Management Plan. People talk about digital twins of the mine. So we're collaborating with a university in Australia. And the idea is here to build the mine as is digitally. So we've taken one of our shafts, we've literally built the mine like that, all the structures, all the stopes, everything in 3D. We've plotted all the brown squares are where we've had all the falls of grounds. In this case, the spheres are where compliance checks have taken place. So we're now putting all the data that we have into that model. So it's things like rock mass data, compliance data, some human behavioral aspects, monitoring data that we have, that we've measured. We're giving it to this model, and then the very clever guys that knows how AI works, this is going to go into a big AI engine, and they're going to see if they can start identifying links or correlations between accidents and what's driving them. The ultimate goal is to say, we want to use that to try and predict whether there's a likelihood of a fall of ground is increasing. Now, for now, we're just looking backwards, like I said. So we've collected all the data and we're going to run that. But going forward, the dream is that you have this digital twin that sits there. As information comes in, real time, it feeds into these algorithms, into this AI engine to tell you what's going on your mine and alert you of the likelihood of something going wrong so that you can react immediately. Instead of waiting for the survey plans at the end of the month to retrospectively have to go back and trying to make the change. So this is the dream. To make use of AI, to make use of very, very powerful databases, to collect all of this information in a single platform to manage geotechnical risk. I think it's possible. I think at the speed that technology is developing, this is going to happen. And it's not too far in the future, where we will have the ability to lighten up the dark or to put a light on the dark spaces underground that we said we like to keep it dark in there. I think the fact that we're getting the connectivity underground, we're going to light up the underground working spaces so that we can get the information in real time to make decisions. Last slide, I had to put in something for the open pit guys. But I think it was mentioned earlier, in the open pit world, where we have an adequate monitoring design that was effectively implemented, we pretty much designed out fatalities. You can speak to the experts in the field. We've literally prevented all fatalities if you've got those things adequately designed, effectively implemented in terms of slope failures. The question is, what is our underground solution for an open pit radar? To make sure we can design out, we can manage not to have any fatalities, that we can get to the point of the dream to say we will cause zero harm to the people working in our companies. And that's it.